Hello everyone. In this video, we will be solving few questions of Cauchy's integral test. So let's see the statement of Cauchy's integral test. It says that if f is a positive monotonically decreasing sequence and integrable function of x greater than equal to 1 such that fn equal to an for all n belongs to natural number, then the series an from 1 to infinity and the sequence in where in is this both converge and diverge together. So for this we require a function. तीन चीज़ें satisfy करनी चाहिए for this. एक positive होना चाहिए, monotonically decreasing होना चाहिए और integrable function होना चाहिए. तो let us suppose take an example. So this is the question. ये question कुछ देखा देखा सा आपको लग सकता है क्योंकि ये क्वेश्चन हम पी टेस्ट की मदद से हम बोलते थे कि पी हार्मोनिक टेस्ट के मदद से हम निकाले थे कि ये कन्वर्ज कैसे करेगा, डाइवर्ज कैसे करेगा. तो सेम क्वेश्चन है, कॉचीज इंटीग्रल टेस्ट देखेंगे. तो इसमें तीन केसेस अराइज हो सकते हैं. फर्स्ट इज केस 1 व्हेन पी इज ग्रेटर देन 1. ठीक है. सो फ्रॉम पी हार्मोनिक टेस्ट वी नो दैट this is actually converge when it is greater than 1 and diverge when it is equal to or less than 1. ठीक है. So keeping that in mind, I am solving it further. So first of all, I have to assume fx is equal to 1 upon x to the power p. क्योंकि कॉचीज इंटीग्रल टेस्ट में हम फंक्शन मानते हैं x को. ठीक है. तो सो फॉर fn is equal to an for all belongs to n. Now यहाँ for x is greater than equal to n, so fx is positive first, monotonically decreasing function second, okay, and also this is integrable function. So this is applicable, so we can write that Cauchy's integral test is applicable. Cauchy's integral test is applicable. Now, so case 1 we are taking where p is greater than 1. So in, what is in now? In is from 1 to infinity 1 upon x to the power p dx. This is in. Now I have to integrate this. Before integrating, just a simple process. Now you know how to integrate this, just do the process and you will get 1 से लेकर n तक over here. Now I am putting the limits in place of x n to the power minus p plus 1 upon minus p plus 1 minus 1 to the power minus p plus 1 upon p plus 1. Now you can see I can take this minus p plus 1 as a common here, minus p plus 1, and I will left with n to the power minus p plus 1 minus 1. Okay, this is nothing but the minus 1. All right. Now this is actually what? 1 minus p. Okay. Now we have assumed that we have taken the case 1 where this is case 1 where p is greater than 1. If p is greater than 1, then this entire value will gives you a negative result. Not sorry, a positive result or a negative result. See, if p is 2 greater than 1 minus 2, so it will give you minus 2. Agreeing or not? Right, it will give us a minus 2. So but I want a positive result because I want something which is positive in the power. Okay, so I may write this as p minus 1. How? If I take, suppose 1 by 1 minus p is common. Now if I take minus common from this side, if I take minus common from this side, I will left with minus minus will become plus and minus 1. Minus 1. Are you agreeing with this step? Now, this will result as 1 upon n to the power p minus 1 minus 1. Now, why we are doing this? Because we have considered that p is greater than 1. So, p minus 1 will give you a positive result. Okay, so that's why this entire thing, this entire power is a positive. Okay, so actually why we are considering this? Because we have taken the limit as 1 to infinity. Sorry, I have written here n, it is infinity. Okay, from 1 to infinity. Wait a sec, here it will be n only, but in the question it is given that 1 to infinity. Okay, this is actually from the definition of Cauchy's integral test. Okay, that if it satisfied both the three condition, positive, monotonically decreasing, as well as integrable function, then we have in such that from 1 to n this fx is equal fx dx. Okay, this is from the definition of Cauchy's integral test. Now we have to put the limit. Okay, when limit n tends to infinity, in is equal to limit n tends to infinity, this whole, in place of infinity we are putting, in place of n we are putting infinity. Now if we put infinity over here and there is a positive result in its power, then this will give you a what? See, infinity to the power something is positive will give you 0. So this will become 0 and this is finite. So 1 upon 1 minus p into 0 minus 1, which gives you a finite quantity. So we can say that this in is convergent, hence this series an is convergent. Now जिस भी स्टेप में आपको कन्फ्यूजन है मैं क्लियर कर सकती हूँ कि स्टार्टिंग से मैंने फर्स्ट क्या किया, यहाँ पर केस 1 p इज़ ग्रेटर देन 1 की हूँ. देन I have seen that this all the three condition is satisfied for the function fx. Okay, so I can write it as in is equal to this. From where I am getting this? From the statement. Let me show you the statement. This is the statement. Okay, so I can write it as this. Now what is the process of convergency of Cauchy's integral test? If you are getting a finite result, as we have seen in the proof section, if my case 1 we have taken this, I have completed the proof part in the video. I will mention that video in my description box. You may refer to that video for better understanding. So we have assumed we have solved this case 1 in which we get the value as a finite. That's why we named it as that it is finite, then it is convergent. And then we have also solved the divergent part where it was not, we are not getting a finite results. So we can say from this that it is finite. If it is a finite, then we can say it is a convergent. And this part actually it was a clear how actually when you put n is equal to infinity here, just forget the power because it is positive. So just forget the power. You can see 1 upon infinity is 0. 1 upon infinity is 0. So write it directly as a 0. Okay. So just forget this. All right. So if we had put infinity in this case, it would be result as infinity. Then this will completely becomes infinity and this case will become as a divergent. Okay, so just keep in mind that in this case, when p is greater than 1, you have to convert this as a positive power. So when you do the positive power, you will get a positive result, that when you put n is equal to infinity, you will get 0. Okay, had it been of different power, it would have result in different number. Had it been of negative power, it would have result in divergency, because the result will get as infinite. Okay, but here we are getting as finite, so in is convergent, then hence an is also convergent. Likewise, we can also take step 2, case 2, that when this p is less than 1. Let me take that step. Case 2, when p is less than 1. Now again, in is equal to 1 to n 1 by x to the power p dx. This can be written as 1 to n x to the power minus p dx. Now solve this, you will get x to the power minus p plus 1 upon minus p plus 1, limit 1 to n. Okay, now n minus p plus 1 by minus p plus 1 minus n minus p plus 1 by minus p plus 1, sorry 1. Now I will take common 1 by minus p plus 1. I'm taking this as a common, and I am left with n to the power minus p plus 1 minus 1. Is it clear till here, guys? You can write it as 1 by 1 minus p, just for the better look, and you can write it as a n equal to 1 minus p here minus 1. Now we have taken p is less than 1. So 1 minus p, if p is less than 1, this will give as a positive result. So there is no need to change the power. Okay, now we will not change its power, because we are already getting a positive power. So no need to change the power, just keep it as it is. Then if you put the limit as n tends to infinity in, you will get limit n tends to infinity. When you will put n as a infinity here, you will get the entire result as a infinity, because it is infinity, then it is not finite, then entire result is infinite. So in diverges, so an also diverges. This is the condition for the divergency and convergency of Cauchy's integral test. Similarly, if you take case 3, that when p is equal to 1, you are getting in is equal to, I'm solving it directly, you get, when p is equal to 1, you will get 1, this 1 by x dx, and this is nothing but log x. Then log x from 1 to n, you know that log n minus log 1. Now log 1 is 0, you know, and log n, when n tends to infinity, this is also give you infinity. Okay, we know that log n tends to infinity, log n give you infinite value. So here also we can say that in is diverges, so an also diverges. So likewise, you can solve the question of Cauchy's integral test. Let's move into different type of question. This is the second question, and in this question it is given that p is positive. Okay, now so what we have, actually we are if you put fx is equal to 1 by x log x to the power p, and fn is equal to an for all n greater than equal to 2. Now in this type of question, you can see that हमारा limit is from 2 to infinity. Now you may ask that why we are taking from 2 to infinity, why not from 1 to infinity? Okay, so The moment you will keep the value of n as a 1, your value will become 0, because log 1 is 0, and this entire process will be meaningless. So we are taking limit as 2 to infinity. Okay, now this type of question you can see in Cauchy's condensation test also, that we will be doing in the next class. Okay, so here from n is greater than equal to 2. Now consider x1 is less than x2. Okay, x1 x2 greater than equal to 2. Now we are taking here two cases, actually two functions. So this is actually fx1 is, from this we can say that fx1 is less than fx2 if we take the function. But let me see, we are just assuming this part. As we have assumed that x1 is less than x2, I can write that 1 upon x1 log x1 to the power p is less than 1 upon x2 log x2 to the power p. Okay, now if we reciprocal this, if we reciprocal it, I will get x1 log x1 to the power p is greater than x2 log x2 to the power p. So from this we can say that fx1 is greater than fx2. So this is wrong. So from this we can say fx1 is greater than fx2. So why we are doing this? Because my dear students and friends, so this is actually, we are solving for Cauchy's integral test. We have to satisfy the three conditions. First, that it is positive. Yes, it is a positive series. There is no doubt in this. Is there any doubt that it is a positive term series? No. So it is a positive term series. Check mark. Second, we have to see that this is a monotonically decreasing. So for the monotonically decreasing function, fx1 must greater than fx2. That's why we have assumed x1 and x2 are the two function, and first we have assumed that x2 is greater than x1. So after this process we can find this fx1 is greater than fx2. So second checklist also done, and this is an integrable function. Okay, all the three conditions are satisfied. So when all the three conditions are satisfied, now we will be proceeding in solving the three cases. First one is for case 1, that is p greater than 1. Okay, let's do it. Now, so in is equal to 1 to n f x dx. Okay, so you can write 1 to n in place of fx, 1 by x log x to the power p dx. If you simplify this, like just take log x to the power minus p and keep 1 by x here dx. Why? Because we will do the integration process, and we know that there is a process known as substitution in integration. So we can see that if we consider log x as a t, 1 by x dx is equal to dt. So this will become dt. This is t to the power minus p. So it will easy for us to integrate this function. So we have to proceed it like that log x is equal to t. So 1 by x dx is equal to dt. So in is equal to 1 to n t to the power minus p dt. So this is t to the power minus p plus 1 upon minus p plus 1 from 1 to n. Sorry, from 2 to n. So it was a mistake. Okay, so this is n to the power. Now you should put the value of t as a log x. Log x to the power minus p plus 1 by minus p plus 1. Okay, 2 to n. Now in place of x you have to put n. log n to the power minus p plus 1 by minus p plus 1 minus log 2 to the power minus p plus 1 by minus p plus 1. Okay, I am taking 1 by 1 minus p as a common. So log n to the power 1 minus p minus log 2 to the power 1 minus p. So here log now again that previous question method, that p is greater than 1. So if p is greater than 1, this will result it as a minus negative sign. Okay, so I am taking a negative sign common and I am writing it as a 1 by log n to the power p minus 1, because p is greater, so I am taking p minus as a common, and this is as it is. Log 2 you can also take here also, not keep it as it is, just take minus common, you will left with p minus 1 from this 1 by 1 minus p. Okay, now um, now if you put limit n tends to infinity here and limit n tends to infinity here, when you put the value of n here, you will see that this is becoming 0. Yes, is there any doubt in this? No. So it is becoming 0 and this log 2 will give you a finite number. You know that log 2 will be giving you a finite number. That's why we have assumed that's why it is being given us that the limit is from 2 to infinity, not from 1 to infinity. Had it been 1 here, it would have resulted as a 0. So this is actually a big no. This is actually correct. If it was a 1, then it would have, it may collapse. So anyways, so this is 1 minus p and this is 0 minus a finite quantity, let's say a finite quantity, or you may write it as this will give you a finite quantity, finite. So iron converges, so an also converges. This is proved. If iron converts, then an also converts. This is actually the basic method of solving this question. Now we have to solve for case 2 where p is less than 1. Okay, if p is less than 1, I have from 2 to n that fx dx as 2 to n. I have log x to the power minus p1 by x dx. Okay, so इतना तक step will be same from this. तो मैं directly वहाँ तक लिख रही हूँ कि log x to the power minus p plus 1 2 to n. इसके बाद ये step भी same ही था, log n to the power, actually I missed this power by minus p plus 1 again minus and log 2 to the power minus p plus 1 upon minus p plus 1. Now here we have imagined that p is less than 1. So if p is less than 1, then this will give you a positive result. Let me first take the common material outside. Now if this is less than 1, then this complete will be a positive number, no need to change the sign, and here also no need to change the sign, 1 minus p 1 minus p. Okay, now if you put the limit limit n tends to infinity, and here also limit n tends to infinity, this n will be becoming as infinity and this complete will result you as a infinite. So this is infinite quantity, and if it is infinite, then what will happen? This will diverges. So iron diverges and an also diverges. Now by the same method, you put the value of case 3, put the value p is equal to 1, you will get this. Similarly, you will get one, like, okay, I'm solving this for you. I'm just solving that part, just the simple part here. Case 3. Okay, that if you put p is equal to 1, this will become log, this will become 1 by x log x, because there is no p. So you have to imagine log x is equal to t, so 1 upon x is dt, so I am getting 1 by t as a result. Okay, from 2 to n dt. Now t is what? Log x. So 1 by t dt, this is going to be log t, the integration, and then log of log x. Are you getting? If we integrate this, I'm getting log t, and then t, putting the value of t as a log x, I'm getting log of log x, and the limit is from 2 to n. If you put n first and put the limit infinity, you are getting infinity minus then 2, then finite number. Infinity minus finite number is infinity, so it is divergent. So likewise, you have to solve the question of Cauchy's integral test, my friends. So this is a very simple test. Actually, if you understand the concept, you can master any question. So just be consistent and just remember the tricks and formulas and statements and the methods. That's all you need to solve these type of problems. Okay, bye bye.